Hello. In this lecture, you will see a few more applications of reduction in order to prove a lot of impossibility results. So, this is on more with reductions. So, one by one, I will give you several examples and I will prove a couple of very important results about undecidability and un-semidecidability. And we will eventually prove that certain languages are not only not decidable, they are even not semi-decidable, that not even recursively enumerable. So, whatever I would say machinery we have so far in our hand, we can do all these things. So let us start with an example without much delay. So here, this is the first example. In fact, what I would like to mention is that we will see three different types of reductions. In many situations, one of these three types works. Okay, so it's good that you understand these three types. So first of all, the first example is about this. Given a Turing machine M, I want to find out whether M accepts the null string. Okay, epsilon. This problem itself is undecidable. Unlike MP or HP, where the input consists of two things, a Turing machine M along with an input X for M, here I am using a language or concentrating upon a language which is defined only by a Turing machine M, or more precisely by the encoding of a Turing machine M. You do not have to worry about or generate the input for M. Okay. So, this is slightly of different type than creating something like M hash X. Okay. In any case, we have seen that the halting problem is undecidable, so I will use a reduction from the halting problem. Now you clearly look at the input-output behavior of the reduction algorithm. Okay. Halting problem requires both a Turing machine or its encoding, to be more precise, and an input W or X or whatever you call for M. The output is a set of Turing machines. Okay. So I will just produce a single Turing machine N. Okay. With the understanding that now the reduction does not have any liability, or for that matter, it is not part of the I would say, duty of the reduction algorithm to produce an input for this. In fact, the input V for this machine N is quite independent of this M and W. It can be just independent of this. It can be anything, because we are only producing this N, not its input. Okay. Now, what did I say when I enclose this M and W inside this N? Is that the reduction algorithm has M and W input to it. Okay. So this arrow is the work of the reduction algorithm. Okay. So it gets some M, it gets some W. It will produce a new machine N. Okay. But this M is a finite amount of information. W is also a finite amount of information. Okay. And this finite amount of information can be stored inside the finite control of the machine N. Okay. So essentially it says how M works. Okay. And what is the input of M on W. Okay. So this information can be embedded in the finite control of N. If you are not that much comfortable, you can assume that this N has two other tapes. Okay. On one of these tapes, okay, this reduction algorithm copies M, how M behaves, and on another tape, it copies W. Okay. And there will be other tapes. For example, one tape for accepting this input V, which is independent of M and W. And this N will work on that. But on these two tapes, the tape containing M is basically a read-only tape because the description of M does not change after the during the working of N. W may be used as as a tape for simulating the working of this machine. Okay, that tape containing W can be used as a tape, and this may be rewritable. Whatever it is, I will henceforth assume that this knowledge of M and W, they are embedded in the finite control of N. Okay, so in order to understand how this embedding is done and what exactly the reduction algorithm does, you just think of each Turing machine as a C program. Okay. So a Turing machine is nothing but a sequence of steps, very elementary steps. Okay. Each transition step is a very, elementary step. Okay. Likewise, a C program can be viewed as a sequence of steps. Like you do some kind of operations, arithmetical logic. You can do some kind of assignment. You can do some kind of, branching based upon some conditions. You can make function calls, return something from a function to a calling function. So these are more natural basic operations for a C program, and all these things can be embedded in the working of a Turing machine. We will see that whatever a modern computer can do, a Turing machine can also do. But anyway, in order to see an analogy of this kind of reduction, think of this M as a C program, okay, which can do something. Likewise, the output N will be another C program. Okay. Now, this machine M, okay, since this is a C program, okay, self-sufficient C program, it has a main function. Now, while you prepare this N, you can use all the functions written in this M, this C program M, including its main, to N. So this copying is not a great difficulty, right? You do not have to analyze the functions or even the main function of N, just copy. But N will be a new C program. Okay. The main for N will not be the same as the main for M. Okay. So what you will do while you embed the notion of M in N, you copy every function and rename the main to something like M main something, or main for M, something like that. And then you write a new main function for this N. And now this W is also to be used by this new machine. So W is basically an input, so you can simply assume that this W is stored in this N as a global array or variable or whatever. Okay. So this is how you embed the information of a C program and, if necessary, of its input into another C program. Then your task or duty is to write a main function for this output program n. Okay, that main function you have to write because you have renamed the main for m to something else, main for m or something. So for this n, in order to be a self-sufficient C function, C program, it should have a main. Okay. So it is the duty of the conversion engine or the reduction algorithm is to write the main for this n, the output C program. Okay. And inside that new main function for n, you can anyway call the main for m. This is basically simulating m on w. So you simply call this capital M, main function for this capital M. Okay. Note that the duty of the reduction algorithm is to read this and this, embed it in the output, okay, with appropriate changes like renaming the main function and writing a new main function for this n. So these are the three things: read, embed this information, and write a main function for this. So these are the things you have to specify. I very, very emphatically say that it is not the duty of the reduction mechanism to actually run m on w. Neither it is the duty of the reduction engine to run n on this v. It only suffices that you can convert this m and w to a description. And the description will assume that this knowledge of m and w are embedded, maybe in the finite control or in case of C programs as functions with the main renamed. It is your duty to write the new main function for n. Okay. So read this, embed this, and write a new main function. Done. Okay, the reduction engine will never run m on w or n on v. Okay, but the main function has to be given. How n will behave when it receives an input like v. Okay. So with this in mind, let us see how this reduction actually goes. So this is a very useful type of reduction that we will use pretty often. So input is m, the encoding of a Turing machine, and w, an input for m, and this is an instance of HP because the reduction is for HP. So the question that I would like to solve is whether m halts on w or not. And the output is a Turing machine that accepts epsilon. Okay, if this reduction is correct, it has to be that the output machine accepts epsilon if and only if m halts on w. Okay. Then the decision of n can be directly transferred to the decision of the halting problem. But since we know that the halting problem cannot be decided, so no decider for this new language can also exist. Okay. So it's something like this. Okay. So n can use m and w in any manner it likes because the reduction engine embeds the information about m and w. Okay. Where we will typically assume these are embedded in the finite control of m, but it is also not a harm to assume that these information are embedded or copied to some tapes or tracks of n. This is also a viable thing, but we will typically assume that this is the case. With a finite amount of information, this can be stored in the finite control of the output machine n. Okay. Now I have to write the main function for n. Okay, this embedding is done, reading is done. Okay, you read m and w, the reduction engine reads m and w, embeds it. Okay, And then I have to write what the main function for n should be. How n works. Okay, the reduction is, again I highlight that reduction engine does not run m on w. It makes no analysis on any function in m or in any function in n. It just produces n. Okay. So let's see how the main function of n will look like. First of all, it has a different input, an independent input v, okay, which has nothing to do with w or m. Okay, it has an independent input v in this context. Okay. So for the moment, it simply erases its input v. Okay. Then it copies w from the finite control where the information of w is embedded. It is copied from the finite control to the tape. Or if it is already copied to this tape, to some tape, then this is not necessary. This is already available in the tape. But otherwise, you copy the finite amount of information about w from the finite control to its own tape. Okay. Then the main function for n calls the main function for m. Okay. That means simulate m on w. Okay. Now, this simulation may halt, it may fail to halt. Now, if that function, main function for m, returns, that means it's a case of halting, then you accept. Okay. What accept? It's not the question of accepting w. The input for n is v, not w. So it's essentially about acceptance of v, which is the input for n, the new machine, which is this v is independent of m and w in this example. Okay. If the simulation halt, accept v. Otherwise, if the simulation loops, you loop. That's all. This is the new main function. Note that this conversion does not require any intelligence. It is just a matter of mechanical copying of some info from the input to the output and writing the new behavior of the target machine. Right? So this is just copying and writing a main function. Okay, there is no further more intelligent thing involved here. And it is what I leave to your imagination, that just a Turing machine without any supernatural capability can do this conversion. Okay. So description of n is all it has to produce in terms of m, w and its own input v. Okay. Well, let us now see that this is actually a correct reduction. What is meant by correct reduction? It satisfies this. N accepts, okay, n accepts epsilon if and only if m halts on w. Okay. So let us see, if m halts on w, then this main function for m will return, okay, which means whatever was the input for v, okay, what was the input v for n, that will be accepted. So if m halts on w, the simulation stops, and in that case the language of n will be the entire of sigma star. Okay. On the other hand, if the simulation of m on w never halts, it loops, then n can never get a chance to come here and accept its input v. In that case, the language of this new machine n will be just empty. Okay, so this is what is written here. So n accepts its input if and only if m halts on w. Okay, whatever v is. Okay, this implies in turn that the language of n is sigma star if m halts on w. It is empty if m does not halt on w. Okay. In particular, epsilon belongs to sigma star. Okay, and epsilon does not belong to phi, the empty set. So in an effort to accept epsilon, I have accepted everything, but that doesn't matter. The behavior of m on other strings doesn't matter. This is a good reduction after all. Okay. So in particular, this says that n accepts epsilon if and only if m halts on w. Because epsilon is here, epsilon is not here. Okay, this is how this reduction works. Okay, now I mentioned that this is quite a general type of reduction. In order to see why, let us see that the same proof can be used for a lot of undecidability problems. So here these are two cases, one is sigma star, one is phi. Okay. So here this reduction uses the fact that epsilon belongs to sigma star, whereas epsilon does not belong to the empty set. Now if instead of epsilon you work with any fixed string like W star belongs to sigma star, but W star does not belong to phi. Okay. So the same question can be answered if I replace epsilon by any other constant string. Okay, this is one thing. Second, you see that many things. This is a finite set. Sigma star is an infinite set. Okay. Okay. Maybe I'll come to that little later in the next example, perhaps. Anyway, let's see. So the decision problem, whether epsilon belongs to this or this. Okay, one time it is yes, one time it is yes, other time it is no. And a very similar set of problems can be solved if on one occasion this is sigma star, on the other occasion it is phi, the empty set. So one is that W be any fixed string like epsilon. It can be anything other, but any fixed string, a constant string. The problem whether a given Turing machine M accepts W is undecidable, like epsilon. Okay, because W is a fixed string, it is in sigma star but not in the empty set. Then you see something like this. The problem whether a given Turing machine accepts any string at all is undecidable. It is basically the same question. Okay. Any string at all. If it is empty set, no strings at all. Otherwise, sigma star, at least one string is there. Okay. Again, if I look at this, the problem whether a given Turing machine accepts all strings, so that reduction is also fine, because in one case I have sigma star, which is the case of all strings. In the other case, it is empty, no strings. Okay. And maybe also something like, the problem whether a given Turing machine accepts only finitely many strings. This is also undecidable. Why? Because sigma star is infinite, whereas the empty set is of size 0, which is finite. Okay. So all these questions can be addressed using this reduction. So it's actually a quite, I would say, generic kind of reduction. Of course, every reduction is a reduction in its own right, but this is a typical kind of reduction, and I mentioned that this is going to be very helpful, this kind of reduction. Okay. So this is how our first example of reductions works. Okay. Now, let us do something slightly more tricky. Okay. But again, this is yet another type of reduction, another genre of reduction that is useful for answering quite a lot of undecidability questions. Okay. So here the input is, once again, I will reduce from HP the halting problem, and I will generate a Turing machine such that thing is little bit, I would say, little bit different in this context. I will come to that. Anyway, let's see. So I will again use a reduction from HB. Okay. The difference between the previous reduction and this reduction is that in addition to embedding M and W, this reduction mechanism produces a new Turing machine which has the information of another constant Turing machine U embedded in it. Okay. So this is U. We will see that this can be the universal Turing machine. Its language is basically the language MP, okay, which is not regular, which is not actually context free, which is not even recursive. Okay. So once again think of this. M is a Turing machine. It has a main function, main for M. This reduction engine will simply copy all the functions of this here, and this W may be stored in a global array. U is a fixed Turing machine like the universal Turing machine. So whatever functions are given in U, they are also copied here, with the only check that no function names match here and here. And the main for M is converted to something like main for M. Main for U is converted to something like main for U. And now it is your duty, that is the duty of the reduction engine, to write a new main function for this target machine N. Okay. So I will choose a language which is not regular. In fact, in order to be more general, we will choose a language which is not context free, which is not context sensitive, which is not recursive. And I will assume that U is a Turing machine, but it is recognizable, Turing recognizable. It's RE, that language. And I will take a Turing machine U, okay, and will embed the information of U in the finite control of the target machine N. Okay. Okay. So let us see. So the input is an instance for the halting problem. That's the machine M and W. I will design a Turing machine N, and if the reduction is correct, then the language of N will be regular if and only if M halts on W. Okay. But in what follows here, I will actually produce a Turing machine whose language is regular if and only if M does not halt on W. Actually, this is the good thing, but I will instead produce a machine N whose language is regular if and only if M does not halt on W. But this is not a very serious thing. Okay. For two reasons I will explain later. The simple thing is that since this is the reduction, then if this machine says yes, then the conclusion is that M does not halt on W. If this machine says no, the conclusion is that M halts on W. It's just a kind of flipping the decision output by N in order to solve the original problem. Okay. So even this kind of reduction will work for proving undecidability. Okay. But this will not work when I prove non-RE-ness. Okay. Un-semidecidability. But anyway, I will come to that later. So once again, N has the information of M and W embedded, maybe in its finite control. Moreover, that extra U machine should also be embedded in the finite controls. Okay. So N embeds the information of another fixed Turing machine. This is highlighted here. I highlight here also. Turing machine U in its finite control. But this is a fixed Turing machine has nothing to do with M. Okay. But what is important is that we require U to have a language which is recursively enumerable but not recursive. Okay. We have seen there are a couple of examples like the halting problem and the membership problem. We have seen that they are recursively enumerable but not recursive. In other words, these problems are not decidable. Okay. So what I will do, I will take the language of U to be this L. Okay. So I will take language of U to be this L. Because it is recursively enumerable, there exists a Turing machine whose language is L. It need not be a decider, or it would not be a decider actually, because this is not recursive. Okay. So this additional U, additional information about U is what differs in this context. Okay. In contrast with the previous reduction. Okay. Okay, so this is yet another sentence saying the same thing. For example, if I take L equal to the membership problem, this language MP, then U can be U is the universal Turing machine. Okay, so now let's see. So this is two parts done, reading M and W, and secondly embedding M and W plus some constant information about U in the finite control that is in the head of the target Turing machine, N. Okay. So I now have to write the main function for N. That completes the rest of the reduction. Okay. So this is the main function. N upon its input V. So this V has nothing to do with an input for M. It also has nothing to do with an input for U, because U's input is not explicitly stored anywhere in the finite control. We will see that actually we will run U on V. Okay. Anyway, that doesn't matter. Okay. So N now has the information of M. It has the information of W, the input for M. Also the information about U. Okay, the transitions of the universal Turing machine. Now it gets an independent input V. How it will proceed. Okay. So for the moment, remember V somewhere on a separate track. This cannot be stored in the finite control because V can be arbitrarily large. Okay. So stored somewhere in a separate tape or track. Okay. Then, like before, you call the main function for M. Okay. Okay, for that matter, you may have to copy this W from the finite control to some tape, not where you have stored V for future use. Okay, write W to the tape and simulate M on W. So this is like calling the main function for M. This may return or may loop. Okay. In the previous example, if it returns, we immediately accepted V. And if this function does not return main function, that means it loops, and this step will never be over. But now I will do slightly little different. If the simulation halts, then I will copy this V to this step and simulate U, the universal Turing machine, on V. Again, this simulation may or may not halt, okay, because U is not a total Turing machine. If this simulation halts, accept. Otherwise, you keep on looping here. So that is the main function for N. Okay. Store V for separate use because I need this V here. Okay. And then first call the main function of M on this stored string W. If that never halts, that simulation, that is if the main function for M never returns, you will never come here. If you come, you simulate the constant Turing machine U on this V, which is stored separately. And this simulation also may or may not halt. If it halts, accept, otherwise reject. And here acceptance and rejection is for something like this for V. It is not W. Okay. So let us see what we have achieved using this reduction. Okay. So N accepts V, its private input V, if and only if two conditions hold. This simulation gets over and this simulation gets over. Okay. Actually, not just that, this simulation gets over and U accepts V. Okay. So it's something like this. If both the following conditions hold, both, this is important. It's not just one. This one and U, this simulation halts and the halting configuration is an accepting configuration. So U accepts and halts on V. Okay. So if that is the behavior of N, then if M halts on W, then N accepts V if and only if U accepts V. Okay. And if M does not halt on W, then this simulation never stops and therefore N does not accept anything. Okay. So I have this. If M halts on W, then N accepts if and only if U accepts. So in that case, the language of N is exactly the same as the language of U, which is L. Okay. And if M does not halt on W, then the language of this is empty, because this simulation never stops and this accept statement is never executed. Okay. So now note that phi is an empty set, which is a regular set, whereas L is maybe something like MP or HP, which is not regular. Okay. So that is the important thing. This empty set is regular, but this is not regular. And therefore, by looking at the decision of N, okay, if N is a decider, okay, but looking at the decision produced by N, I can decide about whether M halts on W or not. Okay. Only thing is that, as I mentioned earlier, here somewhere, this this thing, actually we have produced a reduction where N accepts, okay, N, the language of N is regular if and only if M does not halt on W. Okay. So let us logically justify that this is not a problem. Okay. Okay. So so let L2 be the set of all Turing machine encodings such that the language of N is regular. This is actually a reduction from the halting problem to the complement of L2. Okay. Not exactly to L2. But this is not an important issue. Okay. This will actually prove that L2, there are two ways to defend this. This will prove, for example, that L2 complement is not decidable or recursive. Okay. So first argument is that, so this proves that this is not recursive, L2 complement. Okay. But we know that these recursive languages are closed under complementation. So if L2 complement is not recursive, L2 cannot be recursive. Okay. So this is a second line of proof. Recursive languages are closed under complementation. So if L2 complement is not recursive, L2 is also not recursive. This is one thing. Second, another alternative is, so we have proved that L2 complement is not Agabit reduction. So the point is that L2 complement has a decider if and only if L2 has a decider. Because you take any decider of L2 complement and simply flip the decision, whatever that decider takes, you will get a decider for L2. Okay. So if D bar is a decider for L2 complement, then L2 has a decider that simply flips the decision on D complement. So that way also you can argue. Okay. So use the above reduction and followed by D instead of D complement. This is just an additional step, which is just flipping the decision. Okay. So now you look at this. The language L was carefully chosen so that it is recursively enumerable but not recursive. This implies that this language, okay, in one case this is empty set, which is all of these. It is regular, it is context free, it is finite, it is context sensitive, it is recursive. Okay. Whereas that language L, that fixed language L that you worked with in this reduction, is neither of this. It is neither empty, neither finite, nor regular, nor context free, nor context sensitive, nor recursive. Okay. So this reduction can be used for all these things. Okay. The problem whether the language of Turing machine is finite. Okay. Then whether it's context free. Okay. A regular thing we have proved. Finite, context free, context sensitive, and recursive. Okay. Why? Once again, let me highlight that the empty set is all of this. It is finite, it is regular, it is context free, it is context sensitive, and it is recursive. Whereas that language L is neither of this. It is neither finite, nor regular, nor context free, nor context sensitive, nor recursive. Okay. So once again you see that this example gives a generic kind of reduction. Okay. Therefore, we have been able to prove all these 5 statements, including the original one. I mean, these 4 ones and the new one and the original one. However, this problem, whether the language of a given Turing machine is recursively enumerable, this is trivially decidable because the answer is always yes. Because we are talking about a Turing machine, its language has to be recursively enumerable. So the answer is always yes. Okay. So this is not really an important question to ask. Okay. So now I think I have a little bit of time, so we can look at 2 important theorems. Let A and B be 2 languages which admit a reduction A to B. Then B is recursively enumerable. If B is recursively enumerable, then A is also recursively enumerable. Okay. And if I make a contraposition of this says that if A is not recursively enumerable, then B is not recursively enumerable. Okay. So how do you prove it? It's fairly straightforward. Suppose I want to build a Turing machine for this one, A, given that B is recursively enumerable. So if B is recursively enumerable, then it has a Turing machine. Okay. The language of the Turing machine will be B. Okay. And I want to build a Turing machine for A. So this goes like this. Let sigma be the reduction map from A to B. Okay. And yeah. Okay. So both consist of well, maybe there is some notational problem here. Okay, B is recursively sorry. No, it's fine. B is recursively enumerable. So B has a Turing machine. Let us call it N. So B has to be equal to this of this. Okay. Then I apply the reduction. Okay. Okay. So I will take n equal to something. So I want a recognizer, not a decider, for A as follows. Okay. So on input M, okay, on input W, M does the following. Okay, M uses this reduction map to compute this machine N. Okay, and it runs N on the converted instance. Okay. So actually, this is basically a reduction from the set of instances of A to the set of instances of B. Okay. So using this, so since this B is recursively enumerable, there exists a Turing machine for it, and I want to build a Turing machine for A. So given an input W, I use this reduction map to convert an instance for this language A to an instance for this language B. That is sigma of W. Now N is available. Okay, it's a hypothetical machine. Run N on this. Okay, and simply whatever this decider says or does, do it. Okay. Accept if and only if N accepts sigma W. If it rejects, reject. If it loops, loop. Okay. That's the obvious behavior. And clearly it follows that we have, first of all, this is done by a total Turing machine. This always finishes. So this stage never hangs. If this hangs, okay, it never accepts sigma W. And this simulation does not stop. So that will also not accept W. Okay. If it halts, accept, reject, reject. Okay. So this is what a proof like this goes. And I will actually use this theorem for another reduction. Okay. So once again, let's have the same premises. A and B are languages along with a reduction from A to B. If B is recursive, then A is recursive. Okay. And if I make a contraposition of this, I say that if A is not recursive, B is not recursive. Okay. Why? I will use the previous theorem. If B is recursive, then B is recursively enumerable. That is definitely true. Moreover, recursive languages are closed under complementation. So in particular, B complement is recursive and therefore recursively enumerable. Okay, by the previous example, so if B is recursive and there is a reduction map from A to B, so A is also recursively enumerable. Okay, B is recursive, therefore recursively enumerable. Therefore, by the previous theorem, A is recursively enumerable. Then, recursive languages are closed under complementation. So, B complement is also recursive. Okay. And you see that the reduction map from A to B is exactly the same as the reduction map from A complement to B complement. Why? So, here you have A, here you have B. Things inside A will go inside B, outside A will go outside B. So this is also a reduction from A complement to B complement, right? So it's also a reduction. B complement is recursive and therefore RE. Therefore the same reduction shows that B complement is recursively enumerable. Okay, sorry, A complement is recursively enumerable. Okay. So by the previous theorem again, A complement is recursively enumerable. So what have we proved? A is recursively enumerable, A complement is recursively enumerable, And we have already proved in an earlier lecture that this implies that A is recursive. Okay, both are RE and therefore A is recursive. Okay, so this is a fairly straightforward proof. So now I have situations like this. Recursive languages are closed under complementation. So I have A complement something like this. Okay. Then I have problems like the membership problem or the halting problem, which are not recursive but recursively enumerable. Okay. That means that the complement of B cannot be recursive because recursive languages are closed under complementation. They can also not be recursively enumerable because if B and B complement are recursively enumerable, then B and also B complement are recursive. But it is not recursive B. So its complement must be somewhere outside RE. Now it is also possible that a language and its complement, they are both recursively non-enumerable or non-RE. They are both outside this. Okay. So we have seen several examples of this. Okay, like HP, MP, which are RE but not recursive. Therefore, their complement has to be recursively non-enumerable. Okay. So we will now see some example of this kind of language. Okay. So whatever I mentioned, if A and A complement are both recursively enumerable, then both are recursive. If B is recursive but not is RE but not recursive, like HP, MP, then their complement has to be non-RE. So this immediately says the complement of HP or complement of MP are not RE. And it is also possible that neither C nor its complement is recursively enumerable. Okay. So we will see an example of this type. A language which is not RE, whose complement is not even RE. Okay. So this is such a language. Finite F-fin, set of all Turing machine encodings such that the language of M is finite. Recall that we have proved that this language is non-recursive. This problem is not decidable. But we have not proved that it can or cannot be semi-decided. Okay, Turing recognized. Now I will prove that this is neither this language nor its complement is recursively enumerable. Okay. So we have proved this is not recursive by reduction from HP, but this will not work because HP is not non-RE. So I have to have we need reduction from a non-RE language, and we know that the complement of HP is one such language. Okay. So it's something like this. M, comma W or hash W says that M does not halt on W. We know that this is not RE. Okay. Because if this is RE, then HP will be decidable, recursive. Now we show that, okay, there is a reduction from this to fin and a reduction from this to the complement of this. Okay. Now so one by one I will tell you these two reductions. The first reduction is what we have already seen. Okay. So this is nothing but this reduction is same as HP to fin complement. Okay. Actually, we have produced a reduction from HP to reg complement, regular language complement, but the same thing will work. Okay. So just for the sake of completeness, let me just reiterate. So Turing machine M and input W for M. So this is an instance for the complement of the halting problem. So I would build a Turing machine N such that ln is finite if and only if M does not halt on W. Okay. And as usual, as before, the reduction engine can embed the information about M and W in the finite control of N. Okay. So it's the same reduction. So I just quickly browse through it. It is the input for V. Simulate M on W. Okay, simulate N on W. If the simulation halts, accept. That's all. So in one case, this is sigma star. In the other case, it is phi. Okay. If M does not halt, then this accepts this, which is finite. If M halts, then accepts everything sigma star, which is infinite. Okay. Therefore, you see that this is met. Ln is finite if and only if M does not halt. Okay. So we have already seen this. Therefore, I am not going to spend much time on it. Okay, this is the same caution. The reduction algorithm is not supposed to run N or M. It only creates a description of it. So this is the main function for N. Okay. So this is the final reduction that we will see today. Okay. So this is somewhat tricky. And this is once again another kind of generic way of reducing things. Okay. So once again, the input is an instance for the complement of the halting problem, that is some M, Turing machine M, or its encoding to be more precise, and an input W for M. I will produce a Turing machine N. Now this is a reduction from the complement to complement. So it says that this is finite if and only if this does not halt. Okay. Oh, sorry. If this is infinite, then it's a case of not halting. If it is not infinite, that is finite, then it should be halt. Okay. So this is infinite, that is in this language, if and only if the original thing M, W is in this, that is, this does not halt on W. Or in other words, it is finite if and only if M halts on W. Okay. So now once again, this is a kind of prototypical reduction. So once again, I will use this information of M and W in the head of the finite control of the target machine N. Okay. So do this. Now I have to write the main function for N. Okay. So once again, store V for a separate on a separate track, and on another track you simulate M on W. Okay, but this is not forever. Simulate M on W for exactly as many steps as there are symbols in the input V. Okay, so to be precise, write W on the tape, simulate M on W, not until it halts, but until it halts, or you have simulated N on W for only these many steps. So how do you ensure it? So you have V written somewhere. Okay. So you just simulate one step of M on W, delete one symbol from V. Then go and simulate the next step of M on W, delete one symbol of V. Okay. And if in this process this simulation never halts, you come out. And if in the process the simulation does not halt, even after these many steps, you also come out. So this is not an infinite loop under any situation. Okay. Because you are using the length of V to dictate for how many steps this simulation will run. So this is not an infinite loop. Okay. This will always break. Fine. One breaking is because M halts on W. The other breaking condition is M still does not halt on W, but you have done so many steps. Okay. So this is not an infinite loop, so this will be broken for one of the two conditions. And you know the break condition. If the simulation does not halt in these many steps, then accept. And if it is breaking because the simulation halts on W, then you reject. Okay. So if it does not halt, accept. Otherwise, reject. Okay. So now let us see what language this machine N accepts as a function of the haltability of M on W. Okay. First of all, if M does not halt on W, then irrespective of whatever your V is, this simulation in line 2 would continue until it is broken, because this condition lets the loop to break. It's for these many steps. Okay. So if M does not halt on W, breaking happens because of this timeout happens here. Okay. And this condition hold does not halt in these many steps. So you are going to accept. So if M does not halt on W, then the language of N is nothing but sigma star, which is infinite. Okay. So this is a very, I would say, fine bit of reasoning. This simulation runs until one of the two conditions happens. One, the simulation stops, halts, in which case you reject, or you have run the simulation for these many steps, which is a finite amount of steps. Okay, then you accept. Okay. And if the simulation does not halt M on W, then whatever this V is, the simulation will keep on running, and it will be broken only because you have experienced a timeout. These many steps have been already simulated. So irrespective of V, this is always this accept. So in this case, the language is infinite. If M does not halt, the language is infinite. Infinite if does not halt. Okay. On the other hand, if M halts on W, it halts in a finite number of steps. Let us call this S. Okay, so let me see. Or N. Oh, no, N. Let's say M halts on W after S steps. So, and let's say the size of V, that is the length of V, is N. Okay. If you run this simulation for less than S steps, okay, you do not know whether this simulation is going to halt. In that case, you are going to accept. But if you run this simulation, or if you are prepared to run these simulations for more than S steps, then this simulation will halt. Okay. And then you come out not because of timeout, but because this simulation has halted. In that case, you reject. Okay. So what are these strings precisely accepted here? It is precisely all the strings whose lengths, that is N, are less than S. You accept it because you have not run the simulation for a sufficient amount of time. That is why you found that the simulation is not halting. It would eventually halt. If you give sufficiently many steps, it would halt. Okay. So, if you give enough simulation steps, N greater than or equal to S, then the simulation halts within N steps. So, N rejects V. Okay. Otherwise, if N is less than S, the simulation has not run for a sufficient amount of time. So, N accepts V. So, what is the language of N? It is the set of all strings over sigma star such that the length n of V is less than S. Okay. Now this S definitely depends on M and W, because M is going to halt on W in some number of steps which you do not know. Okay. But whatever it is, if M halts on W, it does so on some number of steps. Okay. That is finite. Therefore, the language of n is set of all strings whose lengths are less than this finite quantity. Okay. This is a function of M and W, but that doesn't matter. It is still a constant. Given M and W, it is a constant, and therefore the language of n is the set of all strings less than a particular length, which is finite. So you see that infinite does not halt. So you see, does not halt, infinite. Opposite is finite, halt. So halt, it is finite. Okay, so that's it. So this is the third type of generic reduction mechanism, which is often proved to be helpful. Okay. In fact, no, regular thing you cannot prove this way. Anyway, fine. So this type of things, so it always simulate M on W, and if the simulation halts, either accept or reject. Okay. Or after the simulation halts, you run another Turing machine. Okay, then accept or reject. And this is the third type of reduction that you see. You run the simulation not forever, but for a limited number of steps. And based upon that, how this simulation terminates because of timeout or because of actual halting, you take some decision. Okay, so that's it. Yeah, so this is the third type of reduction, and in the examples or exercises that you will see, usually one of these three mechanisms, three types of reductions will work. Okay, so we will see several examples like this as mentioned here. So we will solve some of these exercises in our tutorial sessions that are scheduled in the coming weeks. Okay, fine. So I think we have just spent 1 hour. So let us stop. Okay, so we will look at a different topic in the next lecture.